In the last clip, you learned about the shortcut method of oxidation states. In the molecule, for example, let's do the molecule H2CO. Which of these elements are the elements that are closest to the edge of the periodic table and are going to most likely to achieve their preferred oxidation state? And on the right side, it's oxygen. So the oxygen will be -2. But then hydrogen is also the one most electropositive. So it's going to want to become +1. And therefore, the carbon is the element whose electronegativity is in between. Remember, carbon is more electronegative. The electronegativity of hydrogen is less than the electronegativity of carbon, which is less than the electronegativity of oxygen. So carbon's is the intermediate, the middle guy among the electronegativities for the elements. It'll just have to work it out. And as you can see, the oxygen is -2. Oxygen gains 2 electrons. The hydrogens lose. There's 2 of them, 2 electrons. It's all taken care of. The oxidation state for the carbon is 0. And I put a score through it so we can recognize that that's my version of a Roman numeral for 0. Okay, but you have also learned previously the Shor method, of identifying for oxidation states. And in the Shor method, what one does is we draw which uses Lewis structures. And in the Shor method, what you do first draw the Lewis structure. C is the central atom, OH. And in the Shor method, what one does is electrons in bonds for oxidation states get assigned to the more electronegative atom. So carbon is more electronegative than hydrogen. Oxygen is more electronegative than carbon. This oxygen therefore ends up with 8 electrons. It started off with 6. It's -2. This carbon ends up with 4 electrons. It started with 4. It's 0. This hydrogen ends up with 0 electrons. It started off with 1. It has lost an electron. And you can see that the oxidation states of the Shor method should be the same as for the shortcut method. We can then look and figure out the following question. Why is it that the structure of the sulfate ion is the one on the left? And the reason why is, let's draw what we know is the true structure of the sulfate ion. And electrons get assigned to the more electronegative atom. So these are the assignments. All the oxygens have 8 electrons. They're all -2. And the shortcut method, SO42-, we had already figured out that the oxygen was -2 and the sulfur was 6. And indeed, this sulfur has no electrons. It's 6. So the true structure has the Shor method and shortcut method have the same oxidation states. By contrast, look at the structure for SO4 2-, which is wrong. Looks crazy to a chemist just looking at this. But the question is, why is it crazy? It is, in fact, a structure which obeys the octet rule. And the reason why it's crazy is because its oxidation states are wrong. And when two atoms are of the same electronegativity, two oxygens of the same electronegativity, the electrons in the bonds are divided equally. Oops, that's not right. This is the division of the electrons. The sulfur ends up with 4 electrons. It started with 6. Its oxidation state is 2. Well, the shortcut method said it should be 6. This oxygen has 7 electrons. It's -1. This oxygen has 1, 2, 3, 4, 5, 6, 7, and it's -1. The 4 oxygens are -1, and the sulfur is +2. That is just not right. So, knowing oxidation states is actually a powerful tool in finding the right Lewis structure. I leave as a problem for you. We figured out by the shortcut method that N2O4 should be nitrogen in the 4th oxidation state. We can use this to find the Lewis structure for N2O4. And I leave that as an exercise to you.